Well, thank you very much, Professor Chong, for the giving me this fantastic the opportunity to have a talk at this what you say the science talk session. So this is I realize this is more like a TED. So well, but I'm not sure I can behave just such a good as a TED speakers. But anyway, I would like to start. So as he mentioned, I came from this research institute, located at the city of Kawasaki. And he mentioned that Kawasaki has some relationship to maybe motorbike, but actually there's no relationship actually. So the Kawasaki motorbike company, they located in the Kobe city.
Is that right?
Yeah.
Oh, I didn't.
Yeah, because there's a big the heavy industry company, Kawasaki Heavy Industry in Kobe. I don't know the reason why. Maybe it's come from the name of the person. I'm not sure. But this one here is, I will show you the next slide. So I would like to, a little bit talk about where is Kawasaki and the location. So now I think you know this Tokyo International Airport, Haneda Airport. And these are the Tokyo metropolitan area. And this is Tamariba. And here is Yokohama. Maybe you know the Yokohama city, right? And in between Yokohama and Tokyo, here is the Kawasaki city. So this is a real, Kawasaki is sandwiched by Yokohama and Tokyo. And in Japan, if you say Kawasaki city, everybody, realize it's an industrial city. So because the reason is that here, you can see here, these are the Japan's biggest industrial complex. So the city of Kawasaki is, it's really the industrial city. So still there are many, heavy industry companies, mostly the chemical companies and the steel companies and some other companies. However, there's some change in, situation because here, this region here, it's just facing to Haneda Airport. This region used to be the big truck company, Isuzu Motor Company, but they already left to other place. So this region become totally empty. So that means it's a problem for the Kawasaki city because they may lose, tax, and they may lose, the employees, and etc. So the city government decided to make this system make a kind of renovation. So they renamed this area as a King Sky Front. So King Sky Front is designated by the national government as international strategic zone to facilitate the research and development for innovative healthcare business. So they try to recruit, they invite the many, the institutes and companies related to healthcare. So nowadays, as you shown here, we have 66 organizations in this region, and about more than 2,000 people is working. The biggest institute in this region is this one. This is a National Institute of Health Science, that is a Japanese NIH. So surrounding this Japanese NIH, there are many companies like this. So there are even some university, the Keio University. I think the Yonsei has some relationship to Keio, right? So Keio opened some city campus next to our, the institute, and also Tokyo Institute of Technology. They also opened some research facilities. And also some company like Medtronic, you may know this name. Medtronic is a world's largest, medical instrument company. The headquarters is in Minnesota. And also Johnson & Johnson, and several other Japanese companies like Fujifilm Company and some others. And our institute locates here. This is the Innovation Center of Nanomedicine. It locates just in front of the National Institute of Health Science. So now we have many, the accumulation of the, institutes. However, you see, so actually, from office of my window, I always, every day, I enjoy to watch, the aircrafts at Haneda Airport. That's a gorgeous view. But problem is that there is a, river, in between. So also it's quite close, but you cannot swim to the airport. However, very fortunately, the government decided to make a bridge between Haneda Airport to this area, and now it's under construction. So by the Tokyo Olympic game next year, we will have this bridge directly connecting Haneda, the international terminal to our place. So it takes about less than 5 minutes by car. And if you like, you can even walk from, the international terminal to our institute, maybe around by 20 minutes. So I would like to show you some promotion video of this region, which we just prepared. No. So before that, I would like to talk a little bit about what we are doing at this Innovation Center of Nanomedicine. The name is very similar to this center. This is Center for Nanomedicine. So I found out that this center focuses in a very basic research, but our center are more focused on translation research. So the biggest project ongoing in our institute, named ICON, is that COINS. COINS is that Center of Open Innovation Network for Smart Health, which is sponsored by Ministry of Education, Science and Technology. So this project is based on a public-private partnership. So that means that ongoing in collaboration with academia, institute, and industry. So as you see here, in this the COINS project, there are several universities like University of Tokyo, Tokyo Institute of Technology, Tokyo Women's Medical University, and also some other institutes like RIKEN and several others. But also you can see here the several names of the companies. And this orange colored organization have some activity or open the branch laboratory in our institute. So that means that already in our institute, we have not only the academia, but also some companies. We are all in the same building. So what is the purpose of this COINS project? So project goal is, as shown here, the final goal is the development of in-body hospitals by year 2045. That is a year of singularity. So, and of course, to develop in-body hospitals, we have to make this new ideas, new concept and new modalities into market. So we are encouraged to establish the startup companies based on academia industry cooperation. So we already actually the startup, the 2 companies shown here, and another 2 companies are already ready to go. So finally, we'd like to make maybe about a dozen of startup companies from this COINS project, which all focused on some field of nanomedicine. So what does mean the in-body hospitals? So I will show you some video to explain about this in-body hospital concept. It's related to SDGs.
Anytime, anywhere, anyone. Realize an autonomous health society by liberating everyone from diseases of heavy social burden without any regards to psychological, physical, or economic uncertainty. This is not a dream story at all.
体内病院というのはその病気の検出、診断、そして治療というこの一連の行為をスマートナノマシンという、小さい新しいタイプの薬に入れて24時間体の中を循環させることで病気を知らないうちに治してしまうというような仕組みになります。
In-body hospital will not be a dream anymore, so I don't think it will be a dream. It will be a real story within 30 years from now.
Ensure healthy lives and promote well-being for all at all ages, continuing to realize the future and the hopes of people to live healthy and comfortable lives. That is the mission of Coins and our challenge to achieve SDGs.
It's a short video, but you can realize the one of the focus is to develop some tiny, the virus-like nanomachines which can autonomously, circulating our body and doing, sensing and diagnosing and treatment. So of course we cannot make this kind of system so easy, but I would like to remind you of this, the old Hollywood movie that is named The Fantastic Voyage. Do you know this movie? Please raise a hand. No? Oh, you know? Actually, this movie, released in Hollywood more than 50 years ago. Yeah, and so the story is it's a very simple. So this is a vehicle and this is a medical doctor. So medical doctor and the vehicles are shrunk into very small size and send it into our body. So this is the inside of the vasculature, and they travel all through the blood, the compartment, and then reach to the disease site and carried some diagnosis and therapy from inside of our body. So this is really the in-body hospitals. So our, the ultimate goal is to make this kind of system from the scientific fiction to real science. However, of course, recently, this, the kind of our thinking is now, catch interest of the Nature magazine. So it was highlighted as focal point last December as a nano hospital in everybody. So, however, of course, you cannot make this kind of the medical doctor to make this kind of a small size. If I talk about this, maybe everybody think I'm crazy. Yeah. So, however, what I would like to talk today is that we would like to make this kind of the vehicle in a small size, and maybe some kind of the automatic control to accumulate into the anywhere in our body to carry out some task. So, however, the size of this kind of vehicle should be very small. Maybe we cannot make this kind of system just like the assembling a gear or cutting fabrics. So instead of such kind of the top-down approach, we will try to do this kind of system by bottom-up approach. That means that utilizing molecular engineering, that means self-assembly of some molecules to make this kind of system. So my background is a polymer chemistry. So most of the work doing in this project is based on the polymer. So the first thing we would like to do is to integrate many different functions in a single strand of polymer chain, like sensing ability to selectively bind target, operation ability to execute diagnostics and therapy, and processing ability to change structure responding to stimuli. And also, as shown here, maybe we can make this strand to consist of the two different blocks. One may be hydrophilic and one may be hydrophobic. And also, everything should be in better to be biodegradable and better to be biocompatible. So we are mostly focusing on the very biocompatible polymer like polyethylene glycol and polyamino acids. And as Jingmo, introduced me as my background is polymer chemistry. So actually, my background is polymer synthesis, and more, specifically the anionic polymerization. So we utilize anionic polymerization. It's a very fundamental science to design this kind of very sophisticated polymer chains. And after, integrating many functions into single polymer chain, we just put this into aqueous solution in the presence of drugs or nucleic acid or proteins, and they undergoes the self-assembly to make core shell nanoparticles. Sometimes it's really particle, or maybe you can make some kind of rod-like structures or any other structures. And here is just one example of the TEM image of, this is called the polymer micelles, polymeric micellar nanosystems, and it looks like very much like a virus. Actually, the size is around maybe most typically 50 nanometers. And this 50 nanometer size range is exactly same size as hepatitis C virus. So, but this is not virus actually. This is a totally synthetic compound, and importantly, the surface is totally covered by hydrophilic shell. The very, the fantastic thing of this kind of polymer assembly is you just change a small change in a primary structure like this. So this is a junction of hydrophilic block and hydrophobic block. So you just, move this to, to this direction. That means shorten the hydrophilic chain. Then it totally changes the assembled, scheme. And instead of making particles, you can have, in this case, the vesicular structures, like an influenza virus. So based on technology, we are now preparing many kind of different nano systems. And most of the case, the surface is, as I mentioned, is covered by hydrophilic shell of hydrophilic polymer like a polyethylene glycol to exerting stealthiness to avoid foreign body recognition. Maybe you may know that if you are infected by virus, then the immunological function start to avoid this kind of systems. So even though you make this kind of system with a very sophisticated function, even just injecting into body, it will be immediately recognized as foreign body and maybe excrete from kidney or excrete from liver. So first thing we should do is to make this kind of system totally steps. So I would like to show you how it works in this movie. So recently, actually, we are utilizing the in vivo confocal microscopy mainly in the research. So now you can clearly observe directly the inside of the capillary of earlobe of animals. So we are now here is that we are showing, the observing the inside of the capillary of living animals. And here we label the platelets, that is a small, the blood cells, which is, mostly related to the thrombosis formation with green fluorescence dye. And nanosystems, its size is less than 100 nanometers, labeled with red fluorescence dye. So you can see here the nanosystem size is much, much smaller than platelets. However, if you inject nanosystem without stealth layer, what we observe is like this. So you see the red, colored objects, it's almost same size as platelets. So that means it instantaneously undergoes aggregation. And you can see some yellow, the colors. That means these aggregates stick to platelets. So that means eventually what you can expect is that it may cause some embolization or stroke. So that is a very dangerous situation. So of course you cannot inject this kind of system into human beings. However, so if you totally cover this nanosystem with PG, the result is like this. Still, of course, you see the platelets. However, no aggregation. So in this way, we can make this kind of system to have a long circulation properties and other blood circulation. So next thing we should do is to just circulating in the body, it has no work. So next we should do is to integrate some functions. For example, the sensing and entry into target cell and undergoing structural change responding to a signal in the cell, which includes like a change in the pH, or you can give a light, or maybe in this institute, many people are working on the magnets, so maybe such kind of systems. And of course, you can make this system to be, change the structure, sensing the glucose concentration, or ATP concentration, or glutathione concentration. And eventually, it controlling the cellular functions. So this is the whole the idea of nanosystems. So we are mainly utilizing this system for the treatment of cancers intractable by current therapy. So this includes, of course, a metastatic cancer. That is a main cause of cancer death. The many patients die because of the metastasis. And there is some drug-resistant cancer, which is a big problem in the cancer chemotherapy. And also there's some fraction of the cancer cell named cancer stem cells, which is highly intractable cancer cell fractions. And also in some type of cancer, like pancreatic and brain cancers, it's quite difficult for a drug to access to the cancer cells. In case of the pancreatic cancer, because of the sick stroma, and as a brain cancer, it is due to the what we call blood-brain tumor barrier. So we would like to treat this kind of system by nanomedicine. So first thing, maybe you are wondering why this kind of nanoparticles, nanosystems can accumulate easily to solid tumors. And this I would like to briefly mention. That is a tumor accumulation mechanism for stealth nanosystems is a well-known enhanced permeability and retention effect, or we just say EPR effect. So the concept of EPR effect is quite simple. So here is a capillary, and of course in the normal healthy tissues, the capillary wall is totally covered by continuous endocellular cells and continuous basement membranes. However, in the cancer, there's many openings. So that means the virus-sized particle with longevity in blood circulation has more chance to accumulate into tumor by utilizing this opening. So this is quite easy. However, the idea is very easy. However, if you make this into the clinical situation, we are now encountering several difficulties. The number one is that, of course, cancer is a mass. So there not only the extravasation, but you need effective penetration into tumor mass. And sometimes heterogeneity in EPR effect. So especially in a clinical case, or actually some of our developed systems and some other systems developed by others have already been in clinical trials, and we recognize that some type of the cancer or stage of the cancer or patient's individual difference, there is some heterogeneity in EPR. So actually, that imaging is very important, by the way. So, and also, in case of the pancreatic cancer, stroma is a big penetration barrier. So maybe you think the cancer is more like a homogeneous, right? But actually, it doesn't homogeneous. It's very, very heterogeneous. So here is a pathological view of pancreatic cancer. So this region here with a dark, the blue color, that is a cancer cell nest. So that is the cancer cells, the groups. However, these cancer cell nests are totally surrounded by thick stroma with red color. And vasculature only exists in the stroma. So that means that there is no vessel in cancer cells. So that means even if your carrier or if your nanosystem easily, success to extravasate, still they need to, penetrate through this thick barrier to reach to the final target, cancer cells. So this is a big issue. Otherwise, you cannot treat cancer cells in this way. So there may be the three approaches to overcome penetration barrier. Number one is that the size modulation of nanosystems. And number two, second is the use of reagents enhancing tumor permeability. Because of the time limitation, I will not go to this topic. But utilizing some regions, you can normalize the tumor vessels. Then it looks like the inconsistency from this, the enhanced accumulation. But if you see the if there's a the tube with many holes, and then if there are too many holes, there may be collapsed. So that means it has no blood flow. But if you normalize this kind of situation, then there is a the recovery of blood flow. Then you have more the accumulation of nanomedicine. So that is a concept of what we call the normalization of tumor vasculatures. And also, of course, you can use some ligands to inducing active transport. So what about size? So how size affect this kind of the penetration? So this behavior can be directly observed under the in vivo confocal microscopy. So as shown here, we settle the animal here, and then we inoculate the tumor. And we inject the fluorescence-labeled polymeric micelle nanosystem intravenously. So in this way, for example, this is one example. That is a GFP-expressing tumor with a size of around 2 to 3 millimeters. But you can clearly observe each of the, the nucleus of cancer cell, and this yellow vessel, that is the capillaries. So utilizing this system, you can, continuously follow the behavior, the event occurs inside of the pancreatic cancer for almost 20 hours. So I will show you the movie here. So please follow this red arrow like this. So you see some slow opening and slow closing. So what we call this nano eruption, or kind of vent, phenomena. Actually, this is a high-speed movie. So each event takes about 1 hour. So I will show you this in a more magnified scale. That is much easier to observe. So you can see here this kind of nano eruption takes place randomly in many parts of pancreatic cancer. So you see some difference between this 30 nanometer micelle and 70 nanometer micelles. In case of the 30 nanometer micelles, as shown here, so after the eruption, the fluorescence, the intensity diffuses out. So that means that maybe the particle can penetrate inside. But you see here in 70 nanometer particles, after extravasation, the fluorescence dye stays there. So that is no penetration. But actually, this is quantitative results. So in case of the 70 nanometer particle, this is the eruption site. At the eruption site, there is an increase in the fluorescence, but intensity stay high. And there is no increase in the intensity in non-eruption site. But in a 30 nanometer nanoparticle, after eruption, there is some increase. However, it's gone away. So it shows the diffusing of these nanoparticles. And importantly, not only the eruption site, there seems to be some continuous, the extravasation occurs even in a non-eruption site. So to make long story short, so in pancreatic cancer, the small particles can still, penetrate into tumor without any nano-eruption, and then, smoothly penetrate in deep in the tumor tissues. But 70 nanometer or larger particles, its only chance to accumulate is this vent nano-eruption, phenomena, but they just stay in the vicinity of vasculatures and cannot get into the tumor mass. So actually, this is the doxil. Doxil is a doxorubicin-loaded status liposome already in the clinics. So this is the size is around 100 nanometers, and you can see here this is stroma, and after extravasation, it stay in the vicinity of vasculatures and cannot get into the tumor mass. So also in our case, we prepare the polymeric micellar nanosystems with a different size. And this is a change in the tumor volume. You can see the big difference. So only the micelle with 30 nanometer size can successfully suppress the growth of tumors. And actually, based on this result, this is a micelle loaded with platinum compound, platinum-based anti-cancer drug, has already been in phase 3 clinical trial for treatment of pancreatic cancer. They are all control the size to be this 30 nanometers. Now, so this is now the recent progress in clinical trial of micellar nanomedicine, which we have already developed. There are 5 formulations have already been in clinical trial in Japan and also USA and EU. And most advanced one is a cisplatin-loaded micelles, which already been in phase 3 clinical trial. And this one here, that the treatment of head and neck cancer, just started mainly in USA. That is the combination therapy with immune checkpoint inhibitor. That is a combination with Keytruda. The idea is that, of course, immune checkpoint inhibitor therapy is very effective. However, still only maybe 20% of the patients, and the other 80% cannot respond. But if you combine this with a chemotherapy, you can increase the fraction of patients which can be treated by this chemoimmunotherapy. So we are very much looking forward about the progress of this combination of nanomedicine with immune checkpoint inhibitors. And also, importantly, this kind of the clinical trials mostly has been done by this company named NanoCarrier. This is a venture company which we established in maybe it's almost 20 years ago. But already this is in a stock market, and they are now succeeded to raise a fund to carry out 5 the clinical trials all over the world. So, however, there are still the challenge. One of the challenge is to the delivery of the nucleic acid-based compounds. For example, this slide shows a delivery critical issue in siRNA therapy. Of course, siRNA is a very effective as a molecular therapy. However, one of the problems is that it's very difficult to enter into the cell, and pharmacokinetics is very poor. So it may easily disappear because of the excretion by the kidney or treatment in the liver. So we need some good nano systems to deliver the oligonucleotides. So the answer is from in my case, that we got the answer from a very fundamental research. So sometimes if you are hurry to get the purpose, you focus on a very the problem-driven research. But this is nothing from problem-driven research. We got the answer from a very fundamental study. So in about 20 years ago, we are more focusing on fundamental polymer science and mainly the self-assembly of block copolymers. And on that way of research, I found out that we can make this kind of the core shell polymer micelles even by electrostatic interactions. So we just prepare the pair of the block copolymer with anionic charge and cationic charge, and show that just by mixing, we can easily obtain the polymeric micelles with very narrowly distribution. And actually, we first published this in macromolecules and later on the Science. So this is just a fundamental research, but we immediately recognize this can be utilized in application because there are many charged compounds with the delivery issues. For example, the oligonucleotides, plasmid DNA, proteins, and charged drugs. So we utilize this concept for the constructing the nanosystems for delivery. So this is one example. As I mentioned, siRNA or antisense oligo, this is a polyanion. So we're just mixing this with oppositely charged block copolymer or polyethylene glycol and polylysine, and first it forms unit PIC. The smallest, the associates to compensate the charge, and then followed by the secondary association to form polyion complex micelles. So this is a quite stable and buffer. However, the problem is that this may be dissociate back to unit PIC in the blood in the body. So to avoid this, in this case we just introduce a thiol groups to make a disulfide linkage. So disulfide linkage is very stabilized the structure, but if it's however stabilized, you cannot use this as a carrier. But fortunately, inside of the cell, that is a reductive environment. So because of this, because of the increase of glutathione concentration, so this disulfide linkage selectively creep inside of the cell to release the cargo molecules. And also we attach, this is the structure of the block polymer which we prepared. This is the polyethylene glycol, this is the polylysine with SH functionalities. And also we conjugate ligands here. And in this case we utilize a cyclic RGG. So this small cyclic peptide, the reason why we choose is that of course it's overexpressed on various cancer cell surface, but more importantly, this is overexpressed on tumor endothelial cell surface. And this is very important. The reason is that, as I mentioned, you can expect the EPR effect. However, unfortunately, the EPR effect works for some hypervascular tumor. Hypervascular tumor or blood-brain tumor barrier, it cannot expect a strong EPR effect. So instead of EPR effect, we are focusing to use this ligand for the enhanced extravasation. So we prepare the micelle with CRGD and try to treat the glioblastoma, because glioblastoma has a limited vascular permeability due to blood-brain tumor barrier. So first we confirm that rarely we can accumulate this 14 nanometer size particles effectively inside of the brain tumors. So we follow this by intravitreal microscopy. So here the CRGD installed micelles are labeled with red fluorescence dye, and non-targeted micelles are labeled with green fluorescence dye and mixed together. That means the mixed color should be yellow. So we are now observing inside of the glioblastoma, and just after 5 minutes after injection, the inside of the capillary is totally yellow. However, inside of the glioblastoma is totally dark. But 5 hours later, you can see inside of the glioblastoma turns into red. So that means the micelle is only with CRGD can easily extravasate. So these two particles, two micelles, our size is totally same and physical-chemical characteristics is same. So that means you cannot explain this phenomena by paracellular EPR. So this is active transport. So that means that this CRGD are recognized by integrin receptor and stimulate the transcytosis by the active transport to accumulate into glioblastoma. And we utilize this for the treatment of very intractable glioblastoma derived from glioma patients. So we isolate glioblastoma stem cells from patients and then inoculate this again into the brain of the mice and try to treat this by CRGD conjugated polymeric micelles. So in this case, we utilize antisense oligo, which the target the notch-regulated linear non-coding RNA. That means that there is the non-coding region. A non-coding region is very important because it doesn't make any proteins. However, it's all very much related to the carcinogenesis. So one of the such kind of non-coding RNA is 2G1. So we, use this antisense oligo targeting 2G1 sequence. And first, we confirm that there is a selective accumulation, of course, in a glioblastoma bearing mice or CRGD mice, and move into the therapy. So here, there are three, the groups. One is a control. That means that antisense oligo with, the random sequence. And second one is antisense oligo targeting 2G1. And this one here, that is a small molecular compound that is a gamma secretase inhibitor. That means that this also related to the Notch regulated signal. So here is one example. So this is a control. So you see big, the growth of the glioblastoma. However, after the treatment, the glioblastoma size is shrunk in the very small size, and this is the quantitative results. So compared to the control and even to the small molecular compounds, there's a significant reduction takes place for mycelial systems, and there's a significant decreased expression of 2G1. So that means now in this way we can send the oligonucleotides very easily into glioblastoma. However, still we are thinking, okay, so maybe our system is a very many advantage compared to some other system like a PG liposome or cyclodextrin nanoparticle because size is small. But still, we feel this may not be easy to be translated into clinics. The reason is that, of course, still we need more smooth tissue penetration. And another important point is this one, simple process of formulation. So if you decorate your nanoparticle with many kind of functionalities, it's become very much, complicated. And this kind of complicated formulation never move into, the, scale size, the big, scale size, and maybe always problem in GMP production. So we would like to make much simpler system. And recently, we succeeded to prepare that kind of systems. So number one is to reduce the size, comparable to antibody. Because antibody drug is now in many clinics, but it can easily penetrate into many tissues, right? So that means the size of the antibody may be the target size. So we prepared the unit PLC carrier very recently. So I will explain what is a unit PLC carrier. So as I mentioned, from the ion complex of siRNA with oppositely charged block polymer give you the ion complex micelles. However, as I mentioned, this process takes place in two steps. The first step is unit PLC, but usually this unit PLC easily to secondary associate to make PLC micelles. But we consider there may be some way to stop this secondary association, even in a high concentration, and we make this kind of system. So that is matching the number of charge to form unit PLC. That means the siRNA has a 40 negative charge. So we prepare the polylysine with 20 negative charge, 20 positive charge and 2 armed PEG to make this tetrahedral structure, which the load only single siRNA in the core, and the size is almost same as antibody. So I will show you how it works. So again, we utilize an intravitreal microscopy. So in this case, we utilize a fluorescence resonance energy transfer. So if siRNA is intact, we observe the red from this dye to this dye. So we should observe the magenta color. But if siRNA cleaved, then there should be no threat. That means we just observe the blue color. Okay. So here is we are now observing the ERO capillary of animals after injection of free siRNA or siRNA loaded in this unit PIC. So you see here, in case of the unit PIC, it still keep the intact structures, and naked siRNA, degrade within the minutes. So this is the longevity in blood circulation. So compared to naked siRNA, we have a significant improvement in the blood circulation properties of siRNA by loading into this unit PIC. And next is that whether this really accumulate into tumor. So this is the accumulation to pancreatic cancer. You see here that there is a significant accumulation of siRNA into tumor, and importantly, there is almost no accumulation to organ like lung and liver. Most of the nanoparticle has a problem of accumulation to liver, right? But we totally, succeeded to avoid the accumulation to liver and very selectively into tumor. And how about the penetration? So this is the penetration results. Now you can see here that this is a green, GFP expressing pancreatic cells, and this is a cancer cell nest, and red is from Cy5 siRNA, and you can clearly observe the accumulation into cancer cell nest. And this is some quantitative results, and this is a stroma, and this is a tumor nest. And we clearly observe the increased accumulation to tumor cell nest. And this is each, the white circle corresponding to the nucleus of the cancer cells. And you can see here the red color in the vicinity of the nucleus. That means this can, even deliver the siRNA into each of the cancer cells. And so we challenge to treat this very intractable glioblastoma, which we already succeeded by utilizing cyclic RGD polymeric mast cells, and we changed this to this very simple unit PIC. And result is surprising. We observed a significant accumulation into glioblastoma, and very significant knockdown takes place. This is a relative expression of 2G1, and this is a tumor volume. And this is a survival curve. So we got 100% survival over 100 days for 2G1 unit PIC treating mice. And another important point here is that maybe you realize that you don't need any formulation technique. What you do is that here is a siRNA solution, here is a polymer solution, and just mixing, that's all. So this is very simple system and very easy to move into large-scale production. And another important point here is that maybe you may be wondering why this kind of structure can easily increase the stabilities. And maybe most of you are, I believe, the chemistry background. So in a chemistry textbook, you always learn about equilibrium, right? Equilibrium, dynamic equilibrium. So actually, this system undergoes a dynamic equilibrium. So these two looks like same. However, difference is that here, this is a two fluorescence dyes. This is a flat pair, and this is a non-flat pair. And what happens is that like this, always there is the changing of the partners, like this movie. So you can imagine, okay, this kind of system takes place in vitro in a flask, but you may not believe that this kind of selective coupling really takes place inside of our body, but it occurs. So I will show you how to prove this by utilizing this FRET signal. So this is a proof of dynamic pairing of unit PIC under blood circulation. So first, we prepare this, the block polymer labeled with Alexa dye and inject into animal. So of course, there's no FRET signal, so it should be blue. And what we observe is a blue color. Then, following, we inject the acceptor siRNA, and we should observe high FRET, and color immediately changed to red. And then next, we inject a non-labeled polymer. And that means there should be some decrease in PRET signal in between red and blue. That means it should be green. It changed to green. So even in the blood circulation, this pairing takes place. So that means the circulating polymers can directly catch injected naked siRNA in the bloodstream to form unit PIC. So we call this siRNA rendezvous with polymer in circulating blood. So this is a totally new concept. So everybody wants to keep loading substance tightly into nanoparticle and try to deliver to target. But this system is more like a dynamic pairing system. So more like a soccer game. So ball is siRNA, and if they some enemy attack to take out the ball, we just pass ball to another the colleagues, and then deliver into the final target. So actually, this unit PIC system is already in the GMP production, and we are expecting to start the clinical trial in end of this year. Because of the one of the reason is that a very simple formulation, just mixing. Okay, so then what about the intact blood-brain barrier? Of course, the reason why unit PIC can accumulate into glioblastoma is that the glioblastoma has some, still there is some barrier, but there is some openings compared to intact BBB. So that means unit PIC cannot, deliver a cargo into intact blood-brain barrier. So that means that it cannot be utilized for the treatment of neurodegenerative diseases such as Alzheimer's disease. So to solve this problem, we return back to the use of ligands. So in this case, we are focusing on to glucose transporter. The one of the reasons is that the glucose transporter has a significantly high overexpression selectively in brain capillaries. It's about maybe 60 times compared to transferrin receptors. And also, there's already well known that the recognition of glucose by glucose transporter always needs the OH groups at position 1, 3, 4, but position 6, it's open. So we prepared this kind of micelles, conjugated the glucose at the 6th position, and size, designed to be 30 nanometer, and loaded with Cy5 dye. And size is almost comparable to poliovirus. And another trick here is not only conjugate the glucose, but also we control the blood glucose level simultaneously to activate the recycling of glucose transporter from luminal side to abluminal side. So I will show the data here. So we fasting the animal for 24 hours and followed by IV injection of glucose micelles. And only this procedure, there's just a small increase in accumulation to brain. However, if you inject glucose later, then after about 30 minutes, there's a significant accumulation of micelle into brain. Especially this GLUM25 means 25% of PEG is conjugated with glucose. So that means that there is some optimum composition. And accumulation up to almost 6% dose per gram brain. So this is a significant amount because you can see here that some antibody drugs failed in the phase 3, accumulation is less than 0.1%. And the drug delivery systems utilizing transferrin, it's less than 0.4%. So 6% is more, almost 10 or 20 times increase for the accumulation. And important point is that maybe you may wonder, this kind of glycemic control also increases the accumulation to other organs which express GLUT1. But to our surprise, this only occurs in the brain. So other organs, there's no change in the accumulation. And only in the brain, there's an increased accumulation of more than 50%. So this is a brain-specific, the transport. And another, point is that really this system crossing the blood-brain barrier. So we follow this by this intravital systems. So here is after 10 minutes after injection of, the micelle labeled with red fluorescence. So you see the red color only in the capillary, and there's no fluorescence from brain parenchyma. Then 20 minutes, 30 minutes later, we inject glucose, and 60 minutes, we clearly observe the significant fluorescence in brain parenchyma, as shown here. So you can see here, this is a glucose injection, and then 30 minutes, there's a significant increase in the fluorescence intensity in brain parenchyma. And very interestingly, this increase is totally synchronized with a change in the blood glucose level. So this is actually due to the active transport of glucose conjugated micelles utilizing glucose transporter. And we confirm the accumulation of deep into the brain by utilizing two-photon microscopy, as shown here. You see the red spots coming from micelles are you clearly observe even in the deep in the brain. And we clearly see the accumulation of micelle into each of the neurons. This is the 2G1 shown here, where nothing in 0%, 10%, but 25%, 50%, we observe the accumulation. However, you may remember that 25% is the give a best results, right? So 50% is less accumulation. The answer is here. This is accumulation in endothelial cells. So 25%, there's almost no accumulation to endothelial cells, but we observe the significant accumulation for the 50% micelles in endothelial cells. So we think that this is a mechanism. So the ligand with 25%, that is a weak ability. So that means that they can easily pass through this route to release in the other side of the brain. However, if avidity is too strong, it stays in the inside of the endothelial cell, and they cannot be released out from the endothelial cells. So that means that may be the reason why we observe the significant transcytosis occurs for 25% systems, and this is the typical example of what we call multivalent interaction. And of course, we would like to transport the drugs which can be utilized for the treatment of Alzheimer. And of course, there's several strategies. One strategy is to reducing the amyloid beta plaque. And how to do this is to, one approach is to inhibiting expression of A beta forming enzyme to inhibit the plaque formation. So one of the typical enzymes to form A beta is base 1. So we utilize antisense oligo to silencing the base 1 protein production in the brain. So this is a very new data, which already we are still in a manuscript in preparation. So just by single injection, we observe the almost 50% silencing in messenger RNA of base 1 and 30% decrease in ELISA. So that means by utilizing this way, we can selectively silencing the target gene in the brain. And based on this results, we established a new company named Brazon. And Brazon Therapeutics is now laboratory in Kawasaki, and also they just opened their branch laboratory in Boston, BioCentral. to facilitate the collaborative research with biopharma in USA. Now, there may be another approach. Another approach is that the expression of antibody against A beta in the brain, or expression of A beta degrading enzymes. So in this way, maybe we can use DNA or messenger RNA, but we are more focusing on to messenger RNA. So the idea is, of course, it may be interesting to deliver antibody directly into brain, but another idea is to produce antibody inside of the brain from messenger RNA. So why messenger RNA? So one of the reasons is that the following. So by messenger RNA, there's no risk of genomic integration and no need for nuclear entry. This is very important. So especially for the non-viral gene vectors, problem is that you can easily transfect to dividing cells, but there's always a problem for transfect to non-dividing cells. But messenger RNA, you can easily transfect to non-dividing cells. And sustainable protein expression, at least comparing to protein delivery. However, there's some issues. One is the instability under physiological condition, and another is the immunogenicity due to the recognition by toll-like receptors. But these two issues can be solved by package into micelles, because as you can see here, the messenger RNA in the core is totally, protected by PEG shell to increase the stability and also the, avoiding the recognition by toll-like receptors. And another important point here is, of course, in case of this kind of systems, it may easily coat in the endosome, so it may be degraded. So we need some endosome escaping properties in the cell. So to make long story short, we developed this system. This is a very simple structure. This is a polyaspartamide with amino SRM repeats in the side chain. So because this diaminoethan structure is monoprotonated at pH 7, but change into double protonated structure at pH 5 to disrupt the endosomal membrane selectively in endosome, like this. So in the outside extracellular milieu, there's a just a weak interaction with membrane. So that means that you can keep cytotoxicity very low. But in the acidic compartment, it turns into double protonated structure to disrupt endosomal membrane to facilitate the escape into cytoplasm. And cytoplasm pH return back to pH 7.2 to decrease the cytotoxicities. So actually, this is one example. That is a GFP expression in primary neuron. So you can see here the very smooth and uniform expression. And here is a comparison with messenger RNA and plasmid DNA. So for the dividing cells, the difference is just 3 times. But for non-dividing cells, difference is over 35 times. And next, we confirm the expression of messenger RNA in the mouse brain, but this is just a direct injection, and we confirm the expression, and then we move into the production of antibody against A beta plaque inside of the mouse. So first, we focus on the single chain FV because it reduces immunogenicity and efficient diffusion because it is a small size. So we select the sequence of messenger RNA of single chain Fab to selectively bind to A beta oligomer. Okay, but there's another challenge because in case of the E. coli, there's no problem for the excretion of proteins. However, in the mammalian cells, of course, you can produce the antibody inside of the cell. However, there may be no excretion, but there's a way to circumvent this problem. That is we just integrate the human interleukin to derived secretion signal. So in this way, we clearly observe the increased production even in a supernatant of culture, the medium. And then we clearly observe the significant reduction in the amount of A beta oligomers in the mouse. Of course, this is just still the direct injection. But anyway, we can produce antibody inside of the brain from messenger RNA. So our next challenge is to carry out this kind of therapy by systemic injection, by combining this result with glucose conjugated micelle systems. And based on this, we recently found another new company named Acurna, which is focusing onto messenger RNA therapy. Okay, so that means maybe in next era, maybe just not just a drug delivery, but we maybe move into inside to drug production. For example, like the messenger RNA, or even we can send a catalysis, for example, enzyme in this vesicular nanocarriers. So this is the inside of the cancer, and red dot coming from the polymer vesicles loaded with catalyst. That means enzyme. So it's turned into prodrug to active drugs. And what will be the next? So next challenge may be integration of nanosystem into living body and utilize this as a chemical reactor, work as an artificial organelle, and of course, we can make this system to gene repair by nanosystems, like CRISPR-Cas9. So this is one example, collaboration with Jennifer Doudna group in UC Berkeley. So our role is just preparing polymer. So we send this polymer to her group, and they carried out the treatment of Duchenne muscular dystrophy in mice with minimal off-target DNA damages. So anyway, this kind of polymer is quite versatile. So you can utilize this system not only for the plasmid DNA messenger RNA, but you can utilize this for the delivery of CRISPR-Cas9 systems. So I would like to stop my talk at this moment, and finally I would like to express all of my thanks to all my workers and funding agency. So thank you very much for your kind attention.
Thank you for your wonderful talk. And I have a question about the EPR effect.
Yes.
The polymer nanoparticle. So I'm also working on the polymer particle, and I want to hear your opinion about the MPS system, mononuclear phagocyte system, the engulfment of the polymer nanoparticle by the phagocytes. So I know that the polymer nanoparticle's uptake is faster than the EPR effect, but how do you think about this? What is your main opinion? What is the main factor that decides whether to go forward or not?
Yeah, okay. The MPS system mainly in the liver, there's two categories. One is the capture by Kupffer cell, right? So this occurs very rapid. So but it can maybe easily, circumvent by making your particle to be totally covered by, some stealth hydraulic polymer. However, another system is, endothelial cells in liver. So endothelial cells in liver has a very high endocytotic abilities, but this occurs much slow in time frame. So the Kupffer cell, the recognition is fast pathway, but the accumulation to sinusoidal endothelial layer is a much slow process. Usually it takes maybe hour. Yeah, and then to avoiding this, recognition by sinusoidal endothelial layer is more difficult. But even in this case, for example, loaded with some anti-cancer drugs, it can easily, anyway, the mostly, the avoid the recognition by sinusoidal capillaries. But this makes more problem for charged compounds. The charged compound like antisense oligo or siRNA or messenger RNA, even if you cover this with a polyethylene glycol, still it looks to be more easy to be, recognized by sinusoidal capillaries, sinusoidal endocellular layers. Maybe due to the protein, people say it's about the protein corona, so it may, accumulate some proteins.
They should endocytosis
Which system are you talking about?
kind of the self-assembled non-particle charge and isoplatform.
Okay, so the antisense oligo, right? Or siRNA. Yeah, actually, we confirm that this disulfide bond is quite stable under the circulation. Privilege of disulfide linkage is exchanged with, SH group in the proteins. But at least in the circulation, you can totally avoid such a direct attack by proteins. And then after accumulation into some target organ, and of course, if there is some, the reductive environment, then there may be the possibility of the, slow degradation. But always the glutathione concentration is, one order or two order higher in cytoplasm. So we control the, the density of disulfide linkage to not to, dissociate so easily in outer environment. Okay, so that is how do you say, the normal answer, right? However, in reality, situation is more complex. So because nowadays there is a significant, the progress in chemistry of nucleic acid drugs. So still the siRNA has some problem for the entering into the cell, but for the antisense oligo, if you use the so-called gapmer, right? So gapmer can easily penetrate the cellular membrane by themselves. So in this case, you better design your system to be disintegrate before entering into the target cells. Still, it's okay. So it really depends on what kind of molecules you want to deliver. However, in case of the delivery of maybe plasmid DNA or messenger RNA, you have to make this system quite stable, not to disintegrate easily outside of the cell. So actually, one of the the example which I show you, antisense oligo delivery, we are utilizing gapmer. So we cannot exclude the possibility. In this case, there is some disintegration takes place after accumulation before entering into cancer cells. But still gapmer can enter by themselves.
In the lab scale, I can make constantly 5 nanometers nanoparticles.
But 5 nanometer particles, there's a possibility to excrete from kidney. That's all, again, it's depend on the system. So actually, the system which we developed and already in the clinical trial, of course, we overcome such difficulties because everything should be made in a GMP grade, and of course reproducibility and etc. Yeah, but but some particles, if so that's one of the reasons why we switch from because unit pH has almost no problem in formulation process. So in a scientific base, maybe both may be interesting, or maybe the ligand system is more maybe interesting. But if you want to make this into translation, there's another different story, and simple formulation process is very important.
Thank you for the nice I start, and then my question is like all of your particle and then delivery is based on the passive targeting strategy, I guess. And then do you see any difference when you conjugate your particle with some kind of antibodies?
Oh yeah. Of course, we are under CRGG, cyclic RGG, and glucose, that is active target. But one of the reasons why the more passive targeting system is in advance in the clinical trial is that it's much easier to get approval. Because if you conjugate ligands, then the regulation agency asks you to confirm whether such kind of ligand conjugation may change some distribution or maybe some uptake to some other organs, etc. So that's the reason why, as a first step, the passive targeting is much easier. But of course, on the second step, you should consider to use CRGG. And of course, there are many ligands, but cyclic RGG is one of the ligands which can easily be translated. Because already in USA, I believe some group in, I think it's a Dana-Farber Institute or something, they prepared the silicon nanoparticle, 5 nanometer actually. And the center is a fluorescence dye, and conjugated with CRGG. And it get permission from FDA to use for the clinic. I think this is in the clinical trial or clinical research. But anyway, CRGG system has already been approved to use for the human patients. So that means CRGG may be okay. And same for the antibody maybe. Because if you use antibody which already been approved, like a Herceptin or such kind of things, then that is a combination of two things. Usually, if you really want to get approval for new things, if there's two totally new things, it's almost impossible. So next step.
Yeah. All right. I think we enjoyed very much.
Yeah, thank you very much.
Please join me to thank Professor Kataoka.
Yeah, thank you for listening.